Okay, it's great to see you guys here. Looks like we've got most of the class, still not everybody, but that's okay. I'm gonna go ahead and get started. We do have quite a bit to do this week. Let's see, we're getting some weird lighting in here. I'll try to fix that. Much better. All right. So we are back to our normal thing here. Let's see. We're going to pick up, of course, where we left off, talking about curve sketching and then applied optimization. But I wanted to talk a little bit about exam 2 also, because exam 2 is coming up. After we finish the applied optimization section, we will be ready for exam 2. And we've talked a little bit about the curve sketching. I'm going to talk more about that. So I'm thinking that in order to keep us on track, let me come back over here. Exam 2 will be next Monday. Which is the 2nd of November. It's going to cover all the stuff that we've learned since exam 1, and we'll do a review and we'll go through all the topics that are going to be on the exam and everything in detail on Friday. And this Friday is what, the 30th, I think? 31st, maybe? 30th, yeah. Now, what this means is we're not going to have exam 2 graded by the drop date. Remember, the drop date for this class, the last day to withdraw and get a W on your transcript as opposed to a letter grade, is Halloween, the 31st. So if you're nervous about that, if you're having a hard time deciding whether or not you want to stay in the class through the rest of the term, I strongly recommend sending me a Canvas message or coming by setting up a private office hour and coming by that where we can talk something to make sure that you're in a situation where you have all the information you need to make good decisions. Ideally, we'd have exam 2 done before the drop date, but the semester is shorter than normal and we're in the situation we're in. So just if you're nervous, if you're having a hard time making that decision, come see me and we'll talk through it together and make sure that you're able to make the decision wisely. I see there's a question there in chat. Oh, come on. Yep, so we're gonna set this up the same way we did exam 1. There will be a study guide. It'll be published on WebAssign and you'll have to submit the written work for the study guide on Canvas before the test, just the same as there was for exam 1. Yeah, the structure will be essentially identical to that of exam 1, just new material. So today, I want to talk a little bit more about curve sketching, which is one of the more challenging sections in the book. I think this is section 4.5. And if there's time, we're going to get to some applied optimization. But that may have to wait for Wednesday's class. And applied optimization is which section? 4.7. Okay. So the curve sketching stuff is stuff that we should be kind of used to at this point. We've talked a lot about drawing the graph of f prime from the graph of f. We've seen a lot the relationships between a function f and its first 2 derivatives. So how the first 2 derivatives sort of shape the graph of f of x. We're going to go just a little bit deeper, really not even any deeper today. We're just going to be putting those things together. We did one example last week, but I want to do several more examples today just to make sure we're all comfy. So I'm gonna bring up the textbook and I'd like you to take some notes from the textbook briefly. So let me get your text up here. We'll go to book and then chapter 4, section 5. All right. So sketching a curve. We know a lot about how to graph from our algebra classes. Like, you can find x-intercepts by setting the function equal to 0. You can find y-intercepts by plugging 0 in for your variable. We know a lot about end behavior of polynomials and rational functions, right? Finding horizontal or even slant asymptotes sometimes. And those things are enough to sketch some graphs, especially if you plug in a whole bunch of points. But the place we want to get to is a place where we can draw a really nice graph without plugging in a shitload of points. So we know of a few points where important things on the graph happen, like mins and maxes, inflection points, x-intercepts. And then by knowing whether you're increasing or decreasing, concave up or concave down between those points, we can connect them with appropriate shaped curves. So I would like you to write down these things. When you want to sketch the graph of some function by hand, you will first find the domain. So here, I'll show you how I would put this in my notes, right? So guide for sketching graph. First, we find the domain, right? You know how to find domains. Find intercepts and determine any symmetry. And by symmetry here, we mean like, is the function even or odd or neither? If a function is periodic, you definitely want to identify the period. You could put that under here, or you could make it its own thing. Then we want to identify any asymptotes. Now in this class, I'm not going to hold you responsible for slant or skew asymptotes, but I will hold you responsible for horizontal and vertical asymptotes. So item D there would be asymptotes. Or more generally, we could say end behavior. So end behavior for a polynomial, remember, can tell you like whether it goes up on one side and down on the other, or up on both sides. This can be useful in addition to having things like horizontal asymptotes for rational functions, or vertical asymptotes even. The big stuff comes down here. Intervals of increase, decrease, mins and maxes, concavity and inflection points. So where is the function increasing? Where is the function decreasing? This is also where you'll get information about mins and maxes. And then where's the function concave up? Where's the function concave down? This is also where you'll get inflection points. And once you have these things, you should be able to draw a very nice graph of the function. These things together will give you graphs that would rival those published in the textbook, and you can do it all by hand. Now, when in doubt, you can always throw in some more points, right? If this information is still not enough for you to get a good picture of what your function looks like, or if you just want more detail, you can always plug in a few extra x values. Let's look at an example or two. First, are there any questions on how to find any of these things? Some of this, like domains and intercepts, we haven't talked about in this class explicitly, because I'm assuming you remember them from previous classes. Similarly, like even and odd functions, finding horizontal asymptotes. We've talked about that a little bit because we talked about limits at infinity, but some of this end behavior stuff might be a little bit old also. So any questions on how to find any of the things in A, B, and C? Domain, intercept, or symmetries? Remember that an even function is symmetric about the y-axis and satisfies f of negative x equals f of x. Odd functions satisfy f of negative x is negative f of x. This corresponds to y-axis symmetry. This corresponds to origin symmetry. Any questions about the latter three? Do we all remember what it means to find the end behavior? Horizontal asymptotes, limits at infinity, increasing and decreasing, concave up, concave down. This is more recent stuff. All right, if not, then let's get to an example. Let's see, I'd like to use a brighter color for this. Yeah, we'll do x e to the x. This is fun because it's not a polynomial, so it's not something that we learned how to graph really well in pre-calculus. In theory, everybody knows how to graph polynomials quite well, with the exception of finding the y values of mins and maxes. That's not new. But we will do some examples of polynomials. This one is a fun example because it's a transcendental function, right? You've got that e to the x there. So the domain, this piece is a polynomial, this piece is exponential. Both of those have domains all real numbers. So their product has domain all real numbers. Remember, the way I teach domains in college algebra and pre-calculus is to say that you should look out for red flags, right? Like when you go on a date with some guy and he tells you he hates his mom, that's a red flag. You get the fuck away. Functions have red flags, like variables in the denominator, variables under square roots or other even roots, and variables inside logarithms. All of those are some red flags that you need to watch out for. But here we have no variables in a denominator, no variables under any sort of roots, and no logarithms to speak of at all. So definitely no red flags. The domain is all real numbers. Intercepts. To find x-intercepts, we set f of x to 0 and solve. So f of x is equal to 0. Well, f of x is x times e to the x. And then you can set each of those pieces equal to 0 on their own. Either x is 0 or e to the x is 0. This works because these two things are being multiplied. If you have a product of two numbers equaling 0, then one of them has to be 0. X equals 0 that's a meaningful solution. E to the x equals 0 has no solution. You would find the solution here by taking the natural log of both sides. You get ln of e to the x equals ln of 0. The ln of e to the x is just x, so x is the ln of 0, but the ln of 0 does not exist. Okay, so our only x-intercepts come from x equals 0. Y-intercepts, we always find these by plugging x equals 0. So here, f of 0, if I plug 0 in, I get 0 times e to the 0, which is 0 times 1, which is 0. Okay, so the y-intercept is 0. We knew that already, because when we plug in, or when we solve f of x equals 0, we get 0 out as a solution. All right. So the only intercepts, there's only one of them, and it's both the x-intercept and the y-intercept. It's the point 0, 0. Not a lot of information so far. We want to find any symmetries. Is this function even or odd? Is this function periodic? Well, here, f of negative x is negative x times e raised to the negative x, which is just negative x e to the negative x. And this is neither f of x nor the negative of f of x. So this is neither even nor odd. And definitely not periodic, right? There's no trig functions in here. There's nothing here that would make this thing periodic. So we don't have any interesting symmetries. We only have one intercept, and it's both the x and the y-intercept because we go through 0, 0, and our domain is all real numbers. So far, we don't have much at all. No periodicity. Am I skipping over anything? So what's our next thing? End behavior and asymptotes. There are no vertical asymptotes because there is nowhere that x or e to the x blow up to infinity. Vertical asymptotes, remember, are places where the function sort of misbehaves and blows up to infinity. That's usually when the bottom of a fraction is 0 or something like that. The inside of a natural log is 0. So there's none of that going on here. If there were vertical asymptotes, then most likely the domain would not be negative infinity to infinity. So no vertical asymptotes. But if we look for horizontal asymptotes, by taking the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x, here we do get some interesting stuff. So we're looking for horizontal asymptotes now. As x goes to plus infinity, we have limit x to infinity, x e to the x. That's infinity times e to the infinity. E to the infinity is infinity, and infinity times infinity is definitely infinity. So on the right-hand side, as x goes to plus infinity, we don't get anything interesting. We just learn that the function goes up on the right. But on the left-hand side here, I'll have limit x to negative infinity, x e to the x. And this is more interesting. As x goes to negative infinity, that x out front there goes to negative infinity. Well, what does e to the x do?
Go to 0.
Good. And what is negative infinity times 0?
0?
Well, it's kind of a cheeky question. So if we watch the video on indeterminate forms in L'Hopital's rule, was there another suggestion? Yeah.
That one. They just typed it in. Indeterminate.
Oh, sorry. So I couldn't quite make out what that last comment was. But infinity times 0, negative infinity times 0, yeah, this is an indeterminate form, like Andrew said in the chat. This is indeterminate, just like 0 over 0 or infinity over infinity. So in order to resolve this guy, we're going to need to rewrite as a ratio and use L'Hopital's rule. So I can rewrite that limit as lim x to negative infinity. I could leave the x upstairs and shove the e to the x downstairs as 1 over e to the x, or vice versa. Let me try that first. Let's try x over 1 divided by e to the x. This is the same as lim x to negative infinity, x over e to the negative x. Now, as x goes to negative infinity, what does this look like? What's the top doing? Don't leave me hanging. As x goes to negative infinity, what does the numerator here do? Just the top. The top's going to negative infinity because the top is just x. And the bottom?
Positive infinity?
Yeah, that's e to the negative infinity. That's e to the infinity, or just infinity. This is also indeterminate, but now it's an indeterminate ratio, right? Rather than an indeterminate product. So now I can use L'Hopital's rule. And remember, I always like to put a little LH over my equal sign to let the reader know that my next step is using L'Hopital's rule. We're going to take this guy and differentiate on the top and the bottom and try again. That's what L'Hopital's rule says. So I get lim x to negative infinity. The derivative of the top here is 1. And the derivative of the bottom, the derivative of e to the negative x, we use the chain rule. That's e to the negative x times negative 1. Or negative e to the negative x. And as x goes to negative infinity there, the top is now just 1. The bottom is e to the negative infinity, or e to the infinity, which is infinity. And the negative 1 is just negative 1. Well, 1 over negative infinity, that's 0. So our end behavior slash asymptotes, what we have here is as x goes to plus infinity, y goes to plus infinity, and as x goes to negative infinity, y goes to 0. This first bit coming from this first line up here, as x goes to positive infinity, f of x, which is y, goes to positive infinity. So in other words, the graph goes up on the right. And then down here, all this limit work shows that as x goes to negative infinity, f of x, the y values, go to 0. And we needed L'Hopital's rule for that limit on the left. So in other words, our end behavior, if we wanted to just draw the end behavior, we're going up on the right and we're getting close to 0 on the left, something like this. I don't yet know what happens in the middle, but I know if you go way far over here to the left, my graph will be getting close to the line y equals 0. And I know if you go way over here on the right, my graph is going to be pointing up. And now the question is, how do we use the other information we have to fill out the rest of the graph? Well, the other information we have are the domain and the intercepts, and also the derivative information, which is what we're going to do next. So first, any questions on how we calculated or determined what's going on with the domain, the intercepts, the symmetry, and the end behavior? Okay, if not, then I'm going to proceed to take the derivative. F primed of x, well, that's x e to the x all primed. This requires a product rule. This is x primed times e to the x plus x times e to the x primed, which is just 1 times e to the x plus x times e to the x, or 1 plus x times e to the x. So my critical numbers here, the places where f primed is 0 or undefined, there's only one critical number. This is never undefined. And f primed of x is equal to 0 when 1 plus x is equal to 0. Same sort of thing. You set each of these factors to 0. 1 plus x is equal to 0 when x is equal to -1. And e to the x is never 0. So we only have one critical number, and it's -1. I can draw my number line for f primed, plot my one critical number on it, and then test a point to the left and to the right of that number to determine whether or not, or where my function is increasing and decreasing. If I test x equals 0 over here, f primed of 0, if you plug 0 in here, you get 1 plus 0 times e to the 0. That's 1 times 1, which is 1. In particular, it's positive. So f is increasing from -1 to infinity. And if we test x equals -2 over here, f primed of -2, that's 1 plus -2 times e to the -2, which is negative e to the -2. Now, e to the -2 itself is positive. It's 1 over e squared. So negative e to the -2 is negative. So f of x is increasing from -1 to infinity and decreasing from -infinity up to -1. This is the increase and decrease. We also want to get concavity information, right? Concave up, concave down. And that comes from the second derivative. So the same thing we just did with f and f prime, we'll do with f prime and f double prime. I'll take the second derivative. So that's the derivative of 1 plus x times e to the x. Take f primed and prime it again, which is its own product rule thing. That's 1 plus x all primed times e to the x plus 1 plus x times e to the x primed. So what do we get out of this? The derivative of 1 plus x is 0 plus 1, or just 1, plus 1 plus x times the derivative of e to the x is e to the x. So when you put these together, you have e to the x plus e to the x plus x e to the x, and you can factor out your e to the x, and you get 2 plus x times e to the x. So f prime prime is equal to 0. Sorry, that second prime isn't showing up there. F double primed is equal to 0 when 2 plus x times e to the x is equal to 0. This is true if and only if the 2 plus x is equal to 0. So x is -2. And f double primed is never undefined. So now I make my number line for f double primed. This is what will tell me where I'm concave up and where I'm concave down, where I have mins, just where I'm concave up, where I'm concave down. I'll drop -2 on here. To the left of -2, if you plug something like -3 in here, you'll get a negative number, right? If you test x equals -3, f double primed of -3 is -2 plus, or 2 plus -3, that's -1 times e to the -3, which is negative. And if you test something to the right of -2, like x equals 0, f double primed of 0 is just 2, which is positive. So now I've got all the information I need. I'm going to summarize it on one final number line, and then we're going to draw the graph. So I'm going to plot on my third number line all of the numbers from my previous number lines, -2 and -1. Now to the left of -2, that means I'm over here, f is decreasing. In fact, it's decreasing everywhere to the left of -1. So I'll go ahead and fill these in. I'll put some space here to sort of cordon off what I'm writing. Rather than writing f decreasing, I'll just write decreasing, decreasing, and then to the right of -1, we're increasing. Now, also, we know that f double primed is negative to the left of -2, so that means we're concave down. And to the right of -2, we're concave up. So this is information for f. What does that mean? Well, if I go from decreasing to increasing at -1, what must have happened at -1? You guys remember the first derivative test? What does it mean if you go from decreasing to increasing at some number?
It's a minimum.
Good, right? It means you were going downhill before then and you're going uphill after that. That means this must be a local min. And that might also be an absolute min, but it's definitely a local min. Now at -2, I was decreasing and decreasing, so there's no local min or local max there, but I did go from concave down to concave up. What does that tell me?
Inflection point.
Good, an inflection point is anywhere the concavity changes. So I have an IP at -2. I have a local min at -1. The only other interesting thing that you might plot here is 0. Why is 0 interesting for this function? What does this function have at x equals 0?
It's the only intercept.
Good, I've got an x-intercept here. All right. So on your final number line, the number line that you make after making the number line for the first and second derivative, you want to plot all the numbers from your previous number lines and any x-intercepts. Okay, now we're ready to do this. Decreasing concave down looks like this. Decreasing concave up looks like this. Increasing concave up looks like this. So let's draw our graph. I guess before we draw our graph, we should find out what is the y value at this inflection point and what is the y value at this local min. So the IP is at -2. So we need to compute f of -2. Our function f of x is x e to the x, remember? I'll write it here as a reminder. So f of -2, we're plugging into the original, that's -2 times e to the -2, or -2 over e squared. I don't know exactly how big that is, but I know that it's negative. And I know that it's smaller than 1 because e is like kind of close to 3. So e squared should be kind of close to 9. So this should be kind of close to 2 over 9. And my local min, what is the min value there? That's f of -1. That's -1 times e to the -1, or -1 over e. And again, I know that e is kind of close to 3, so this is kind of close to -1/3. All right. So let's draw our graph. First, I'll put in the end behavior, which I know is up on the right and getting close to 0 on the left. Then I'll put in my only intercept, which is this guy. If I had other intercepts, I would put them in as well. Then I'll plot my inflection point and my local min. My local min is at -1, and my inflection point is at -2, so I'll mark those off on the horizontal axis. The local min at -1, we said is about -1/3. So if I put -1 as a y value down here, that local min should be somewhere around here. And the inflection point at -2, we said was at about 2/9, which is -2/9, which is definitely smaller than 1/3. So he's gonna look like this. Here's my IP, here's my min. Since this is a local min, I know nearby he looks like this. Since this is an inflection point, I know that I have to be concave down on that side of it and concave up on this side of it. And now if you put all these pieces together, you can get a really nice graph. You know, it should curve up here. You can say it's going to look something like this. And this is a really good drawing of this graph. This graph has all the good stuff. It's increasing where it should be, decreasing where it should be. We have an inflection point here and a min here. It's got all the right asymptotes and all the right end behavior. It is a good graph. Now, is it perfect? No. Does it need to be perfect? No. If we wanted to make it better, could we? Yeah, we could plot a bunch of extra points. But let's compare this to what Desmos draws. Let's go Desmos graphing. Not bad, right? Not bad at all. Now their graph goes up much more steeply on the right than mine does. But notice at -2, we've got this inflection point where we go from concave down to concave up. At -1, we've got this local min. At 0, we've got the intercept. And the horizontal asymptote on the left is y equals 0. The end behavior on the right is going up. So this is a pretty good graph. And again, we could make it better by adding more points. But this is about what I'll be expecting from you guys on the test. I want inflection points labeled clearly, mins labeled clearly. So we should come in here and say what this point is. This is -2, -2 over e squared. This min is -1, -1 over e. And this intercept is 0, 0. As long as you give me these things, I'll be really happy. And the good news is that when it comes to things like polynomials and rational functions, you get great results with this. Any questions on the techniques we used here? Okay, let's try another example then. I'll grab one from your textbook. Yeah, we could do that. That's a little boring. That's the one we just did. How about, we'll go back to that first one. I was thinking a polynomial would be nice here, but a rational function, that's okay. So we're going to graph 2x squared over x squared minus 1. We're going to do the same sort of thing. We're going to start by finding the domain. Here we do have some red flags. I've got all this variable stuff in the denominator. So 0 is equal to x squared minus 1 when? When is the bottom 0? When is this function undefined? Well, that's x minus 1 times x plus 1. So this is, the bottom will be 0 if and only if x is 1 or -1. Thus our domain is all real numbers except for those. That's -infinity to -1, unioned with -1 to +1, unioned with 1 to infinity. That's my domain. Everything except those numbers which make the function upset, which make the bottom 0. Intercepts. Well, the y-intercept, let's do the x-intercept first. That's how we did it last time. X-intercept comes from setting f of x equal to 0. That means I take my whole function, 2x squared over x squared minus 1, and set it equal to 0. Well, this thing is only going to be 0 if the top is 0. The only fractions which are 0 are those which have 0 in the numerator. So this is the same as just saying 2x squared equals 0. which is the same as saying x equals 0. So my x-intercept is again the same as my y-intercept. We're going through the origin. But just for completeness, if I wanted to find the y-intercept, I would plug x equals 0. So here f of 0 is 2 times 0 squared over 0 squared minus 1, which is 0 over negative 1, which is 0. Although we already knew that from solving for the x-intercept. Asymptotes and end behavior. Vertical asymptotes, this time I do have some. Those come from when the bottom is 0, right? If the bottom is 0 and the top is not 0, then you have a vertical asymptote. So here we have VAs at x equals -1 and x equals +1. Those are the two places where this function blows up to infinity. Horizontal asymptotes, here the limit as x goes to infinity of f of x is the limit as x goes to infinity in 2x squared over x squared minus 1. And we talked about how to take these limits back in section 2.6. Does anybody remember the trick for calculating a limit like this? If you wanted to, let's be clear, if you wanted to, you could use L'Hopital's rule. Here, both the top and bottom are going to infinity. So you could use L'Hopital's rule, but you don't need it. We had a special name for the trick that you need here, the trick that you can use. We called it renormalization. You divide top and bottom by the largest power of x, and you'll get 2 over 1 minus 1 over x squared. And as x goes to infinity, this goes to 2 over 1 minus 0, or just 2. And the same thing happens at negative infinity. We would again renormalize, and then 1 over x squared goes to 0 as x goes to negative infinity also. So our end behavior on both sides is approaching the line y equals 2. I don't yet know what goes on in between. I do know that I go through the origin, but that's all I know so far. I also have vertical asymptotes. We said at -1 and +1. So this might give me a slightly better feel, but we still want to know, where is this function increasing, where is it decreasing, where is it concave up, and where is it concave down? One thing before that, we'll look at symmetries. Here, f of -x is 2 times -x squared over -x squared minus 1. And the square of -x is the same as x squared. So this is 2x squared over x squared minus 1. And that's the same as the original function. So since f of -x is equal to f of x, we learn f of x is an even function. So the graph will have y-axis symmetry. So now that we have all that information, we can take the first couple derivatives, make some number lines, figure out where we're increasing and decreasing, and draw our graph. Are there any questions about these steps? I'm just gonna do that. So. Okay, I'm gonna turn on my fan real quick. We will look at the increasing, decreasing, and concave up, concave down. So remember our function there is 2x squared over x squared minus 1. So f primed, this requires the quotient rule. That's low d high, so x squared minus 1 times the derivative of 2x squared minus high d low, so the top 2x squared times the derivative of the bottom over low, the denominator all squared. Taking the little derivative pieces here, the derivative of 2x squared is 4x. So this is x squared minus 1 times 4x minus 2x squared times the derivative of x squared minus 1 is 2x. All over x squared minus 1 squared. We can simplify. This is 4x cubed minus 4x minus 2x squared times 2x. That's also 4x cubed. All over x squared minus 1 squared. So the 4x cubes go, and you get negative 4x over x squared minus 1 quantity squared. That is f prime. And we need to figure out where is this positive and where is this negative. The critical numbers are x equals 0, because that's when this top is 0. So f primed is 0. And you might think plus and minus 1 are critical numbers because that's where f primed is undefined. Right? This comes from f primed of x equals 0. And f primed of x undefined would give us x equals plus and minus 1. But remember, a critical number has to be in the domain of the original function, and our domain here does not include 1 and negative 1. So these are not critical numbers. Because they're not in the domain. So remember, a critical number is a number that's in the domain of the original function and makes f prime 0 or undefined. Plus and minus 1 do make f primed undefined, but they're not in the domain. So they're not critical numbers. My only critical number is x equals 0. So my number line for f primed contains just x equals 0. To the left of 0, if you plug in something like negative 1 or negative 2, you'll see that this function is positive. F primed is positive if you plug in, say, negative 1, because the top would be positive 4. Oh, not negative 1. Negative 1 doesn't work. You plug in negative 2. Plug in your favorite negative number in the domain. Now, there's a question in chat here. When would something be undefined but in the domain? So you have to be careful about what function you're referring to. A critical number can be a place where the derivative is undefined, but is in the domain of the original function. So like square root of x or cube root of x, all of those have derivatives with x's downstairs. So x equals 0 is a critical number for the cube root of x because it makes the derivative undefined, but it's in the domain of the original function. So you're right, if a number makes a function undefined, it cannot be in the domain of that function. But we're talking about two different functions here, f and f primed. So Josh, in answer to your question again, to be a critical number, making f primed undefined, you need to also be in the domain of f, not in the domain of f primed. Does that clear that up? Okay, cool, yeah. Yeah, you raise a good point there. All right, so if I were to test -2, f primed of -2 is, oh, I got +8 over 9. This is definitely positive. And over here, if I were to test +2, I would have -8 over 9. Or sorry, -8 over, yeah, 3 squared, 9, which is definitely negative. Now we're going to take another derivative. So this tells me that my function is increasing everywhere to the left of -2, or increasing everywhere to the left of 0, and decreasing everywhere to the right of 0. All right. So this was all of our work for increase and decrease. And now we'll do the work for concavity. F double primed. This is going to be a little bit messy. I have to take -4x over x squared minus 1 quantity squared and prime that whole thing. Again, I think a quotient rule is the way to go. So downstairs I'll have x squared minus 1 squared all squared, which is x squared minus 1 to the 4. And upstairs I'll have the bottom times the derivative of the top, which is x squared minus 1 squared times the derivative of the top is -4, minus the top, which is -4x times the derivative of the bottom. And the derivative of the bottom requires the chain rule. That's 2 times x squared minus 1 times the derivative of the inside, which is 2x. So here is f double primed in all of its gory glory. We can distribute and simplify as much as possible. So this is, I've got x squared minus 1 all squared. That's x to the 4 minus 2x squared plus 1 times -4. The two minuses here can make a plus 4x. What else do I have here? I've got 2 and 2x, so I can write that as 4x times 4x times x squared minus 1. All of this is still over x squared minus 1 to the 4. And then finally here, I'll distribute the last bits and combine. Maybe I'll distribute over here and then combine in the line below. So this is going to be -4x to the 4 plus 8x squared minus 4. And then here I'll have 16x squared times x squared minus 1. So that's 16x to the 4 minus 16x squared. And all of this is over x squared minus 1 to the 4. Pens hate me today. All right, so if we combine our like terms, I've got -4x to the 4 plus 8x squared minus 16x squared, that's minus 8x squared. Oh, I also had a plus 16x to the 4. Damn. All right, sorry. 16x to the 4 minus 4x to the 4. That's 12x to the 4. Yeah. So that's these two. And then these two are minus 8x squared. And then minus 4 is just minus 4. So here's my second derivative. And I need to figure out where this thing is 0 and where it is undefined. F double primed, just like F primed and F, is undefined at plus and minus 1. That's from these factors in the denominator. The numerator, I can factor out a 4. And I get 3x to the 4 minus 2x squared minus 2. And this can be factored by thinking of x squared as the variable. So this is like 3x squared squared minus 2x squared minus 2. So to factor 3x to the 4 minus 2x squared minus 2, we sub u equals x squared. Then this becomes 3u squared minus 2u minus 2. This can be factored with the AC method. A times C is -6. So we need two numbers whose product is -6 and whose sum is -2. Now, can we think of two such numbers? Product is -6, so your only choices are like 3 and 2 or 6 and 1. I don't believe any of those add up to -2. No. So these inflection points are nasty numbers. Let me just have a quick check here on the second derivative and make sure I'm not losing my mind. 12x squared plus 4. It looks like I did make an error here somewhere. Something should have canceled that didn't cancel. Yeah, thank you. Thank you. It looks like there might have even been, let me come back here.
Can you have canceled out x squared minus 1?
Oh, we could, couldn't we? Yeah, if we come back to this step, I could have factored in x squared minus 1. It should have still worked out fine either way, though. So low d high, minus high d low, 2 times that to the 1 times 2x. So this is correct. Here, when we FOILed that out, instead of FOILing that out, we could have factored an x squared minus 1 to cancel with the bottom. Let's come back to that step and do that. So if I factor in x squared minus 1, this will save me a meaningful amount of work. What's going to be left in the numerator? Here there's one copy of x squared minus 1 times -4. And here there was only a single copy of x squared minus 1 to factor out, so there won't be any left. And we'll have minus -4x times 2 times 2x, which would be 4 times 8 times 2 is 16. So plus 16x. That's still not going to come out the way that they have it here, right? Did I make a mistake? Plus 4x. They have this as a plus 4x. Oh no, that's correct. Yeah, minus, and then 2, and then x squared minus 1 times 2x. No, okay. I'm just being silly. So what do we get here? Minus makes plus. 4x times 2 is 8x. 8x times 2x is 16x squared. And all of this is over x squared minus 1 to the 4. We can cancel one of these x squared minus 1s with one of these. And we'll get x squared minus 1 times negative 4 plus 16x squared over x squared minus 1 quantity cubed. Now distributing this 4, we'll have negative 4x squared plus 4 plus 16x squared. Over x squared minus 1 cubed. So f double primed, if you combine these, it is 12x squared, yeah, okay, plus 4 over x squared minus 1 cubed. So maybe there wasn't an error in that previous work until we got to this factoring step, because this stuff is correct. Okay, rather than hunting that down and wasting your time for my own ego, we'll work from here. So f double primed is 0 when 12x squared plus 4 is 0, but this has no solutions, right? If you subtract the 4, divide by the 12, then you'll be taking the square root of a negative when you go to isolate x, or if you factor this over the complex numbers, you'll discover that the roots have a non-zero imaginary part. So there's no solutions. And f double primed of x is undefined at x equals plus and minus 1, but these are not in the domain. So our number line for f double prime doesn't actually have anything on it. There's nowhere f double primed is 0, and there's nowhere f double primed is undefined, which is in the domain of my function. Nevertheless, we'll draw a number line for f double primed. And let's include our vertical asymptotes, the minus 1 and the 1, and we'll just check each of these regions for concavity. If we check at 0, f double primed of 0, we'll get 4 over negative 1 cubed, which is negative. If we test at, say, 2, then we would have 12 times 2 squared. 2 squared is 4, so that is 12 times 4 is 48, plus 4 is 52, is definitely positive. And downstairs here, we would have 4 minus 1 cubed. So I'll write it here, test x equals 2. F prime primed of 2 is 52 over 2 squared is 4 minus 1 is 3. 3 squared, sorry, 3 cubed is 27. So f double primed is positive over here. And using symmetry, if we test at negative 2, we'll find that f double primed is positive over here as well, because this is an even function. So while we don't have any inflection points, the concavity does change over the vertical asymptotes. And this is a somewhat subtle thing. Normally, when we're talking about critical numbers, places where you could have a min or a max, those can't happen at places where the original function is undefined. Because in order to be a min or to be a max, there has to be a point on the graph. This kind of looks like we have inflection points at plus and minus 1, but we don't because, again, there isn't a point on the graph. Nevertheless, the concavity changes. Think about the graph of 1 over x. On one side, it's concave up. On the other side, it's concave down. There is no point where the inflection changed. There is no point where the concavity changed But as you jump over that vertical asymptote, you came back with a different shape. So when you're sorting out concavity, it's wise to also include anywhere that the original function is undefined on your number line, even if they shouldn't be critical numbers for f primed. So now we have our two number lines, our number line of increase and decrease, and our number line for concavity. We can combine this information into a single number line. So I'm going to come here and I will plot all the numbers that are on any of these, which are -1, 0, and +1. See if we can fit this in here. So everywhere to the left of 0, f prime is positive, which means we are increasing. And everywhere to the right of 0, f primed is negative, which means we are decreasing. To the left of -1, f double primed is positive, so we are concave up. Between -1 and +1, f double primed is negative, so we are concave down. And to the right of +1, we are concave up again. So here's the number line for the shape of f of x. All that good stuff in it. Over here, to the left of -1, we are increasing concave up. That looks like this. Between -1 and 0, we are increasing concave down. That looks like this. 0 to 1, we are decreasing concave down. That looks like this. And 1 to infinity, we are decreasing concave up. That looks like this. We had a vertical asymptote at -1 and a vertical asymptote at +1. So there can't be any mins, maxes, or inflection points there. At 0, what's going on? What sort of feature does the graph have at x equals 0? It's got to be a local max, right? Because we go from increasing to decreasing. So this has to be a local max. We should find that max value. The max is at x equals 0. And f of 0, we actually sorted that out earlier. That's 0. That's also our intercept. It's our x-intercept and our y-intercept. So now we're ready to draw our graph. I'm going to come up 1, 2 units and draw in my horizontal asymptote. And we should label it. The horizontal asymptote is the line y equals 2. I'm going to come left and right 1 unit and draw in my vertical asymptotes. And just like we do for the horizontal ones, we should label them as equations of lines. The only point I know for sure is on the graph is the point 0, 0. And I know that that's a local max. So the behavior nearby has to look like this. Now over here to the left of -1, in this region, I am increasing and concave up. I know I need to be settling down on this horizontal asymptote, y equals 2. And if I am increasing concave up, that means I need to be doing this in this region. Since I have a VA here and I know I'm coming down like this, or by thinking of this as being the increasing concave down shape everywhere between -1 and 0, I can conclude that my graph must look like this. And then we can just use the y-axis symmetry to complete it on the other side. We know that this function is an even function. So if you reflect this stuff over here, you get this. Or you could apply the same sort of logic that we used on the left. And that gets you, again, a mighty fine graph of this fairly complicated rational function. The thing that's new, the thing that you couldn't do in pre-calc that you can do now, I guess there's really two of them. In pre-calc, sometimes you would have a weird squiggly shape in the middle here, right? Or maybe over here, a weird squiggly shape. And it wasn't clear exactly where that squiggle was. Concave up, concave down thing. Finding the inflection points will now solve that problem for you. Also, you know that you've seen graphs like this where this whole vaguely parabolic, although it's not a parabola, but this kind of bowl-shaped thing is moved down or up, or you have another one over here. Now you can find the exact min and max values in these bowl-shaped pieces, which is nice. In practice on an exam, I'm most likely going to give you either a very simple rational function or a polynomial function when it comes to this curve sketching problem. The things I care about most are that you can find extrema, mins and maxes, and that you can find inflection points, because that's the new stuff. Everything else you should have hopefully learned well in pre-calculus, but we'll be testing for all of them and they'll all be equally weighted. And if you remember your pre-calc, focus on finding mins, maxes, and inflection points, and just practice getting comfy drawing graphs. How are we doing for time? If there is time, I would love to do one more, but we are just 4 minutes over now, so I'm going to have to stop. Next time, we'll do one more example of this curve sketching business, where your goal is to come up with this line that's got the shape of the graph in each of these regions. And down here, you can identify any mins, maxes, or inflection point, and then drawing this graph. I'll do that for a trig function or two next time. And then we're going to talk about applied optimization, which is where you take the min-max problem and you solve it in a real world setting. So you want to figure out what's the most efficient way to build a container that's got, minimal surface area, but as much room inside, all of that sort of thing. And then we'll be ready for exam 1. Remember, sorry, not exam 1, exam 2. Remember, exam 2 is going to be next Monday, the 2nd of November. And I will go ahead and push out the study guide for that today, although I recommend that you work on the homework problems before the study guide. All right, if you want to come see me, I will have a normal office hour this afternoon, 3:30 to 4:30. Otherwise, I wish you guys the best and I will see you next time. Take care.